Imagine pressing any key on your keyboard. In just a few milliseconds, millions, even billions of electronic operations happen before that character appears on your screen. So, what really happens inside your computer? Let's find out. Before we continue, here's the secret behind every computer. It understands only one language, binary, just 0 and 1. Why? Because inside every computer are billions of tiny electronic switches called transistors. Each transistor can have only two states, on or off, represented as 1 and 0. By combining these zeros and ones in different patterns, a computer can represent everything from a single letter to photos, videos, games, and even the operating system. When you press a key on the keyboard, the keyboard's matrix detects the exact row and column of the pressed key. The keyboard's microcontroller then identifies which key it is and looks up its corresponding scan code stored in its memory. Finally, it sends this scan code to the computer as a stream of binary data, zeros and ones. The keyboard's microcontroller sends this binary data through the USB cable to the motherboard. From there, it is forwarded to the CPU for processing. The CPU passes the scan code to the operating system. The operating system interprets the scan code and converts it into the corresponding character. Displaying a character is just one example. Whether you're opening an app, playing a game, editing a photo, or watching a video, the computer processes every task using binary, millions or even billions of zeros and ones every second. Now, let's go a little deeper. A single transistor can only act as a switch. But when multiple transistors are connected together, they form logic gates such as AND, OR, and NOT. Although AND, OR, and NOT are the basic building blocks, most digital circuits are actually built using two special gates, NAND and NOR. They're called universal gates because any logic gate can be created using only NAND gates or only NOR gates. Let's see a real example. When you calculate 1 plus 1 in the calculator app, the application sends the addition request to the CPU. Inside the processor, this isn't solved like a human would solve it. Instead, combinations of logic gates work together to perform the binary addition and return the result. Whenever your computer performs arithmetic operations such as addition, subtraction, multiplication, or division, the CPU uses arithmetic circuits built from logic gates. At the core of these circuits are adders, which are used directly for addition and also help perform the other arithmetic operations. Arithmetic operations are just one of the many tasks the CPU performs. It also compares values and makes logical decisions. Comparison operations such as greater than, less than, or equal to, along with logical operations like AND, OR, and NOT, are all carried out by digital circuits built from logic gates. By combining billions of these logic gates, the CPU can run programs, play games, browse the internet, edit videos, and perform countless other tasks. Logic circuits are the brain behind every calculation and decision inside a computer. But a computer needs much more than logic circuits to function. It also requires memory to store data, buses to transfer information, clocks to synchronize operations, input devices to receive commands, and output devices to display the results. Only when all these components work together does a computer become fully functional. For example, suppose you enter 1 plus 1 in the calculator application and press the equals button. The CPU first loads the two numbers from RAM into register R1 and register R2. These values are then fed into the logic circuits inside the ALU, where the addition is performed. The result is stored in another register, R3. If the program needs the result later, it is then written back to RAM and displayed by the calculator application. So far, we have seen how the CPU stores data in registers and performs calculations using logic circuits. But who tells the CPU what operation to perform? This is the job of another important component inside the processor, the control unit. The control unit acts like the manager of the CPU. It doesn't perform calculations itself. Instead, it continuously fetches instructions from RAM, decodes them to understand what they mean, and sends control signals to the appropriate parts of the processor. These control signals tell the registers when to load or store data, instruct the ALU which operation to perform, and coordinate the movement of data throughout the CPU. Just as the ALU is built from specialized digital logic circuits for performing arithmetic and logical operations, the control unit is also built from digital logic circuits. Its job is to decode instructions and generate control signals. Rather than processing data, it coordinates the movement of data between RAM, registers, and the ALU. This ensures that every operation happens in the correct sequence. The control unit works in a continuous cycle. It first fetches the next instruction from RAM and decodes it to determine the required operation. It then generates the necessary control signals, loads the data into registers, and instructs the ALU to execute the operation. Once complete, the result is stored in a register and written back to RAM if needed. This process repeats billions of times every second, allowing your computer to execute programs efficiently. At the same time, the control unit keeps track of the program counter, which stores the address of the next instruction to execute. After one instruction is completed, the program counter is updated, allowing the control unit to fetch the next instruction. This process continues until the program finishes. But there's one question. How does the CPU perform billions of operations every second in the correct order? The answer is the CPU clock. The CPU clock generates billions of electrical pulses every second. Each pulse acts like a heartbeat, synchronizing the processor's operations. The control unit receives these clock pulses and uses them as a timing reference to coordinate the instruction cycle. It fetches instructions from memory, decodes them, generates the required control signals, and coordinates the movement of data between the registers and the ALU. When you open an application, it is first loaded from your SSD or hard drive into RAM. Before accessing RAM, the CPU first checks a high-speed temporary memory called the CPU cache. The cache stores frequently used instructions and data, allowing the CPU to access them much faster. The required data is then loaded into the CPU's registers for processing by the ALU. This entire process, from storage to RAM, cache, registers, the ALU, and back, happens continuously while you use your computer. Whether you're typing a document, browsing the internet, playing games, or editing videos, billions of transistors work together to process data in just fractions of a second.